All right, so it should come as no surprise that we can also form a sampling distribution of means. So when we talk about means, we might have a parent population that looks something like this, and its mean would be abbreviated as mu, and its standard deviation as sigma. So this pile of numbers might represent, for example, I don't know, bowling series scores for professional bowlers. Average series of 762 with a standard deviation of 84. And I've just drawn a very random distribution here, a random discrete distribution. So what we're going to do is reach into this pile, and we're going to take samples of size, in this example, 49. So we're going to reach into this pile. We're going to grab 49 bowling series totally at random. We're going to average them together. And then whatever average we get, we're going to turn that into 1 grain of sand and throw it on this pile. So we'll do that millions and millions of times. Theoretically, we do it for every possible sample. And by the way, the number of possible samples becomes astronomical really fast. So in this case, whatever the population size is, it could be millions. We would raise that to the power of our sample size, and we just get these like head-explodingly large numbers. So there are many trillions upon trillions of grains of sand in here. So again, we stack them up, and they're going to form a particular shape. So we need to be able to describe 3 things about it. What is it shaped like? What is its mean? And what is its standard deviation / standard error? Because these are samples that we're piling up. So when we look at this distribution, it's the sampling distribution of means. Our x-axis represents x bar sample means. All of those sample means have some mean, collective mean. So we call that the mean of the means, mu x bar. And all of those means have some collective standard deviation. The standard deviation of the sample means is called the standard error and is abbreviated like that. How can we, what can we conclude about those 3 things? Shape, size, shape, center, and spread. All right, so let's take them one at a time. And again, the mean is going to be the intuitive one. If I'm drawing from this population has a mean of 762. If I gathered many samples from this population and then threw them onto a pile, what do you think? Where do you think most of them would be centered? And if you said 762, you're right. That one's intuitive. So just like the case for proportions, the collective mean of all the sample means equals the population mean. The mean of the means is the mean. As far as the measure of spread, the width of this curve, the error of the sample means is again not intuitive, so we just need to memorize this formula. And again, it's short and simple. The standard error turns out to be the population standard deviation over the square root of n. So in this example, that population standard deviation again was 84, right? The sample size n was 49. So we just have to plug those numbers into this little formula. So here I've plugged in sigma is 84, n is 49. The square root of 49 is 7. That's why I picked 49 actually, because it's simple. And 84 over 7 would be 12. So notice that the standard error, 12, is much lower, much smaller than the standard deviation of individuals, which was 84. We're gonna hit on that concept a little more pretty soon. But essentially what it says is that samples cluster around the mean much more tightly than individuals do. And that's really important. Again, I guess I'll defer that discussion for a few more minutes here. But in the meantime, let's also discuss the shape of this sampling distribution. And this property is called the central limit theorem. As I've indicated on my lecture notes here, the lecture outline. The central limit theorem says the mean of the means is the mean. The standard error is sigma over the square root of n. We just calculated that. And the shape of this distribution is basically close enough to normal as long as one of the following two things occurs. Either the parent population is normal or the sample size is at least 30. You don't need both, you only need one. If the parent population is normal, it doesn't matter how big the sample is. If the sample is large enough, it doesn't matter what the parent population looks like. But one of those things needs to occur in order to use normality. So if we go back and look at our example, let's see what conditions apply here. Is this parent population normal? No, it's a total random mess. It's a discrete pile. Looks like junk. Okay, well, is the sample size at least 30? Oh, yes, it is. 49. That constitutes a large sample for these purposes. So since we met that condition, we don't need the other one. One of these conditions alone will guarantee that the sampling distribution stacks up in a normal curve. I want to close out this clip by discussing this note regarding sample sizes before we move on to some examples together in the next segment. So if we look at these formulas for standard errors, the standard error of proportions is the square root of PQ over n, and the standard error of sample means is sigma over the square root of n. Even though these are very different concepts, you might notice that these formulas have something in common, and that is that they both have a square root of n on the bottom. Now, why does that matter? Okay, so let's think about what happens when n gets larger, increasing n, when we take larger and larger samples. Now, think about how fractions work. If you put a larger sample size on the bottom of a fraction, what happens to that fraction? Larger denominator means smaller fraction, right? 1/100th is much smaller than 1/2. So, as we take increasing sample sizes, both of these standard errors decrease. Now, what does that mean? When a standard error decreases, remember the standard error is a measure of spread. And if that's decreasing, it means that the distribution is doing this. It's getting narrower and narrower and narrower. So what? Why does that matter? Because what it's telling us is that when we take samples that get larger and larger, they tell us more about the parameter. They become better guesses, right? They're not spread out all over the place. They tend to cluster towards the middle. Therefore, since we won't really know what the middle is, they become better and better clues. In fact, they kind of approach this central limit, don't they? Hence the name central limit theorem. Okay, it's a really key concept. Increasing the sample size n decreases both standard errors. So for large n, large sample sizes, the sample statistics cluster very tightly around their parent parameters, giving samples excellent predictive value. That's kind of the magic trick of statistics, if you think about it. Now, interestingly enough, there is a counter consideration, and that is that the narrowing happens more slowly than the sample size grows. The reason for that is because the bottom of the fraction is not n, it's the square root of n. The square root of n is a lot smaller than n itself, right? So for example, the square root of 100 is only 10. So what that's telling us, if you look at this formula, you might think, oh my gosh, if I just take bigger and bigger samples, then those samples will become better and better guesses for the parameter. So why don't I just make n really huge, like 100? Well, because as it turns out, if you make your sample 100 times larger, then this standard error only narrows by a factor of 10. Sample 100 times larger, predictive power only 10 times better. So we don't want to get too carried away because it gets harder and harder and more expensive to take samples that are really huge. So as it turns out, most good samples end up being in the ballpark of about 1,000. That turns out to be a really good balance between precision and sampling expense. So keep your eye on that. Whenever you start seeing, I'm recording this in an election year, 2024, and so we're going to be seeing a lot of news about surveys. And when the next time you see an article about a survey, take a look and see if you can find the sample size. And I'll bet you it'll probably give you something between 300 and 3,000. They're almost always in that ballpark of 1,000 if they're good samples. Another thing to be aware of is that these formulas, neither one of these formulas has a capital N in it. Capital N is the population size. Now, a lot of people kind of scoff at election surveys. They say, oh my gosh, the United States is so large, you can't figure out the United States with a sample of 1,000 people. That's just such a tiny sliver. Come on, give me a break. These statisticians are just fools. Well, as it turns out, the formulas don't depend on capital N. It doesn't matter how large the population is. That is not an issue. So if you're statistically sophisticated, you can turn around and tell them, well, hey, look, pal, the standard error of a sampling distribution is not dependent on capital N. So, it's a non-issue. Again, that's kind of a magic trick of statistics. So you could have a population of basically infinite size, and you can take a sample of just 1,000, and that sample will tell you a lot about the population, assuming, of course, that it was chosen randomly. And let me make maybe one final comment about that issue too. At the beginning of this course, we discussed the fact that a sample is a good reflection of a population as long as it is, one, large enough, which is an issue we're seeing now today, and two, random enough. For the rest of this course, we're basically going to be assuming that the samples are random enough. In the real world, that's always an issue. I understand that. But for the purposes of learning about the statistics, we're just kind of focusing on the large enough part now. So again, from here on until the rest of the class, that's kind of an unstated assumption. We're just assuming that all the samples we choose are chosen really, really well and really, really randomly. Okay, so that's enough about the theory behind sampling distributions. Let's go on and do some examples together.